Hello. So we're now going to be looking at the sort of exam questions where they ask you to calculate the amount of mass that's missing, for example, in a process like fusion or fission. I've got a very simple example for us today. So we're going to start off with something that you might not realize. And I've got a little picture of a scale here, and I'm weighing or measuring the mass of a proton and a neutron, and they're not the same, which might seem a little strange to you because so far we've just said that protons and neutrons have the same mass. They almost have got the same mass, but it's not exact. So the mass of the proton is almost the same as the mass of the neutron. So to deal with this, and also to deal with the fact that the numbers that we have to use are incredibly small, the mass of a proton is 1.67 times 10 to the minus 27 kilograms. What we do is we introduce something called the Unified Atomic Mass Unit. And actually, when you're looking on a periodic table and you're looking at the atomic mass, those numbers are actually in the Unified Atomic Mass Unit. The atomic mass unit is on your data sheet that's given to you in the exam, and 1U equals 1.66 times 10 to the minus 27 kilograms. So if we look at the mass of a proton, it in kilograms is 1.67 times 10 to the minus 27. Or, a little more simply, it's 1.00728 U. Now that's a number you don't have to remember. That number is going to be given to you in any question that you need, or whenever you need it. And then comparing with that, you can see that the mass of the neutron is slightly more. The mass of the neutron is 1.00867 atomic mass units. So we can use this to answer questions. And in fact, this is quite a common thing on our specification. And the sort of question that you might get is something like this. Let's say, how much energy would be released if a helium nucleus was split into its constituent parts? Well, if we were to work that out, we would need to use E equals mc squared to find out how much energy was associated with the mass that's missing. We're not going to do that step today. We're just going to look at how we would go about working out this mass difference. And we're going to do that in kilograms. So any question like this would have to give you some data. So this question tells you that the proton has a mass of 1.00728, neutron 0.0867, and the helium nucleus itself, which you should know is made of 2 protons and 2 neutrons, has a mass of 4.00151 U. So really all we have to do is work out what the mass of 2 protons and 2 neutrons is and compare it with the mass of the helium nucleus and see what the difference is. So I've done that over here. Okay. I had a little bit of a mistake on the top line, so ignore that weird gap. So the mass of the 2 protons and the 2 neutrons is adding the numbers up in that table. It comes out at 4.03190 U. The mass of the helium nucleus is 4.00151 U. That was in the data table. So we can find out what the mass difference is. And the difference between the two, subtract those two numbers, is 0.03039 atomic mass units. Now, most questions would then go on to say, what is it in kilograms? So you multiply that number by 1.66 times 10 to the minus 27 kilograms. And again, that's on your data sheet. So the missing mass, or the mass difference between a helium nucleus and its constituent parts, is 5.046 times 10 to the minus 29 kilograms. It's very small, but it is significant. And what you could do then is work out how much energy that's equivalent to. So if you use E equals mc squared, you could multiply that mass by the speed of light squared, and it would tell you the amount of energy involved as well. Okay, thanks.